the audience knows why G-torsors are a wonderful thing, but maybe I should recall for the others why anybody cares about G-torsors. So let's see, the setup is usually that G is an affine group scheme over a finite type over a field. It's roughly what you might call an affine or linear algebraic group over a field. Although I want to allow this to be non-smooth, which is an issue in characteristic P. In other words, it could be non-reduced. That's another way to say it. Okay, and then a so definition is that a G-torsor over a field, which, so even if we start with a group over one field, we want to consider bigger fields too, F containing K. That means, say, an affine scheme in this situation, X over K, with an action of G, or G base changed up to this bigger field, over this bigger field, such that one way to say is that if you go further to the algebraic closure of F, G acting on X becomes isomorphic to just an obvious action to G over the algebraic closure acting on itself by translation, by left translation. So in other words, it's like you're studying group actions which over the algebraic closure become a completely obvious group action. People use different terminology for this, like you could say that this is a free transitive action of G on X, or that this is the same thing as a principal G bundle over spec F. Okay, let's see, so there's this notation, H1 of F comma G means the set of isomorphism classes of G-torsors over F, which is a pointed set because there's an obvious G-torsor, which is just sort of G itself viewed as a G-torsor. Say that. There's not a group or anything in general. It's an abelian group if G is abelian. Okay, and just as some sort of background for what I'm saying, these G-torsors, because this means the algebraic closure of F, these are G-torsors that are locally trivial in the FPPF topology, technically. So if G is smooth, then they're also locally trivial in the étale topology. But if you're dealing with group schemes that are not smooth, then this more general notion is I would argue, the natural notion of a G-torsor. Okay, so let me give a few examples, not to spend too much time on this, but let's say, so for example, if just G is a finite group, which you can view as an algebraic group over any field you like, then say H1 of KG is just homomorphism, the group of continuous homomorphisms from the Galois group of K. That means the Galois group of the separable closure of K over K into G up to conjugation by elements of G. So for example, like H1 of K with Z mod P coefficients is the group of cyclic Z mod P extensions of your field by Galois theory, or in general, this is roughly the set of extensions of your field with Galois group G, roughly, except that the homomorphism might not be surjective. And in particular, an example that will come up occasionally is that H1 of K with coefficients in the symmetric group. This classifies étale algebras over K. And étale algebra just means a finite product of finite separable field extensions, in this case of degree n. So sort of at least the main or the most interesting part of this would be the set of isomorphism classes of separable field extensions of degree n of your field. Maybe I should say this is a more general point about why torsors are interesting. Basically, if you want to classify any kind of algebraic object over K, if the automorphism group of that object is a given group, G, then G-torsors classify algebraic objects of that sort. And there are a few more examples of that. Say H1 of K with coefficients in GLN. Well, to describe that in the same way, you have to think of some algebraic object whose automorphism group is GLN, and there's an obvious one, namely vector spaces of dimension n. So this could be viewed as the set of vector spaces over K, or if you prefer vector bundles over spec K of dimension n up to isomorphism. And of course, there's only one such thing, so this is just one point. Right, so principal GLN bundles over schemes are vector bundles over schemes, which are interesting, but over a field, they're kind of all trivial. So in some sense, a lot of this theory is sort of focused on properties of G bundles over fields as distinguished from the properties over more general topological spaces or varieties. Okay, so some other sort of familiar examples like that are, if I take Q0 to be a non-singular quadratic form over a field, you can look at the orthogonal group of that, the group of linear maps that preserve this quadratic form. And so this H1 group, by a similar argument, can be viewed as the set of quadratic forms of the same dimension. If Q0 has dimension n, then the set of torsors for that orthogonal group classifies all the quadratic forms of dimension n over K up to isomorphism. Okay, so those are some sort of classic examples that basically motivate why people are interested in classifying torsors. Okay, let me do one example that's sort of special to characteristic P here. So it's sort of visible. So another, yeah, example, as sort of a typical group scheme in characteristic P, let mu P be the subgroup scheme of the multiplicative group, so GL1 if you prefer, such that x to the P equals 1, sort of over a field of characteristic P. You could consider this in any characteristic, but let me focus on field of characteristic P and look at the group scheme of P roots of unity. So let's see. So this sort of, as a scheme, it's kind of, maybe it doesn't look like much. So you have the multiplicative group has this element 1, and this is sort of kind of like Pth infinitesimal neighborhood of 1. As a set, it's just 1 point, but as a group scheme, it has order P because the ring of functions here has dimension P as a vector space. Okay, so in that case, what are mu P torsors? Well, to analyze it one way, we have an exact sequence of group schemes over little k, involving this and the multiplicative group, UP to the multiplicative group, and then this is taking the Pth power to the multiplicative group. This is exact sort of in the relevant sense for me, which is in the FPPF topology. So that means that, for example, like what does it mean to say this map is surjective? It just means that like over an algebraically closed field, every non-zero number has a Pth root. Yeah. So, right, and so this gives a long exact sequence of cohomology, which basically allows you to analyze mu P torsors. So like, I guess the relevant part will be, so H0 of this with coefficients in a field is just this group of K points of the multiplicative group, or K star. You take Pth powers, that goes to the same thing. And then you have H1 of K with coefficients in mu P, and then H1 of K with coefficients in the multiplicative group. And this can be viewed in a couple of ways. I mean, like, this is the group of rank 1 vector bundles over K, which for a field, or one-dimensional vector spaces over K, which, as I said, is just 1.0. And so this explains what a mu P torsor over a field is. It just classifies elements of your non-zero elements of your field up to Pth powers. Okay. Right. Maybe I'll just do one more sort of classic example along those lines. Again, sort of that field. Again, take a field of characteristic P, and what do I want to do? I want to analyze the group of Z mod P torsors over K. Again, this is positive. So in this case, to analyze Z mod P, there's a different exact sequence of group schemes over K, which is involving Z mod P, and now the additive group. And the additive group where this map is like X goes to X to the P minus X. So notice that because we're in characteristic P, this is X to the P, for example, is a homomorphism of additive groups. And yeah, and the kernel of this map is basically just the elements of Z mod P. Those are the only ones for which X to the P equals X. And again, this map is onto in the relevant topology here. Okay, so again, you can use this to analyze Z mod P torsors over a field of characteristic P, and along the same lines, and what you get is that H1, and again, here H1 of the additive group is 0. It's an easy calculation, if you like. So using that, you find that the group of Z mod P torsors over a field of characteristic P is, how can you describe it? It's sort of K points of this group, I guess, modulo the image of this map, which is the set of elements of the form a to the, like X to the P minus X, such that X is an element of K. Yeah, okay. So, and then of course, this is called Art and Schreier theory. But it's sort of just from this exact sequence, you get this calculation of the Z mod P torsors. And this you might call Cromer theory. Okay. Okay, so that's supposed to argue that torsors are a good thing. Yeah, what are cohomological invariants? Again, I'll sort of describe that hopefully a bit briefly in the sort of the non-characteristic P setting, and then get on to the characteristic P business. Okay, so yeah, so the thing is that one wants to classify G-torsors, and in cases like, say, the orthogonal group, this is sort of very far from being a solved problem. For sort of general fields, we don't have a meaningful classification of quadratic forms. So in order to classify such things, people study, or Serre introduced the notion of cohomological invariants. So let's see. Let's say, so in this situation, if G is an affine group scheme, a cohomological invariant for my group scheme G over field K is a natural transformation of functors from the functor H1 of Fg, where this is a functor on fields F containing little k. So you want to go from there to some cohomology group like Hi of F with coefficients in, say, Z mod M of J. This is étale cohomology or Galois cohomology, if you prefer. And then, yeah. Okay, so that's sort of the definition. Yeah, for some given values of I, J, and M. Okay, so in other words, yeah, it's just a cohomological invariant. It's sort of like a characteristic class for G bundles, except that we're only considering G bundles on fields. So this has a kind of, you could consider sort of invariants like this for G bundles over any variety or something, but then it would kind of be too much like the theory in topology to be that interesting. Because we're only interested in G bundles over fields, this has a kind of distinctive flavor. Like, yeah. So, yeah, and then one writes like, so for example, the group of invariants for in sort of any bi-degree over field with, or sorry, I should just be written over the field of say GLN is just 0, I guess. Well, maybe I should say this is equal to Hij of the base field. Where this is my notation for something like Hi of the field with coefficients and well, some coefficients twisted by J. In étale cohomology, by the way, this would mean like the J tensor power of the nth roots of unity, of the nth roots of unity. So in other words, what I'm saying is that the cohomological invariants for GLN are basically trivial. They're all sort of like constant invariants because essentially all GLN torsors over fields are trivial. So, if we were considering like bundles over more general algebraic varieties, this wouldn't be true. There would be invariants for GLN bundles, namely Chern classes. But over fields, those all become zero. And so you just have these sort of, I hope it's clear why elements here give you a cohomological invariant. It's just the kind of cohomological invariant is just a constant invariant where you sort of map every G-torsor to basically the same element there, meaning an element that comes from the cohomology of the base field. Okay. So the idea is this is kind of a boring case. An interesting case that Serre worked out, I believe, was the orthogonal group. Yeah, so let's say if you take K to be a field of characteristic not 2, then the invariance over that field in any by degree for the orthogonal group of some quadratic form, yeah. So let Q0 be a quadratic form over the space field and of dimension n. I always mean a kind of non-singular quadratic form. Right, so if I look at invariance in any bidegree with coefficients in Z mod 2 for the orthogonal group, I get something kind of nice. So you get sort of the cohomology of the base field, which sort of has to be in there as like constant invariance. And then you have a free module over that with basis the Stiefel-Whitney classes, W1 up to Wn. So here, you know, how shall I view this? So invariance for this particular algebraic group, because it's sort of H1 of the orthogonal group, that can be just viewed as the set of isomorphism classes of quadratic forms of dimension n. So basically what we're asking here is to compute this group means asking what are all the possible cohomological invariants for quadratic forms of a given dimension. And this is sort of the answer. In particular, these Stiefel-Whitney classes, which maybe were defined by Milner, others in the 60s, so let's say Stiefel-Whitney classes, if I think of it as invariants of a quadratic form, some other quadratic form, Q of dimension n over a field capital F, which will also be of characteristic, sorry, the same characteristic. The Stiefel-Whitney classes, I want to say, lie in H, I get this right, HI, say WI of a quadratic form lies in HII of the base field of coefficients in Z mod 2. So this means, sorry. Yeah, I think this is the correct way to say it. Yeah, I mean, it's actually, sorry, the second index just doesn't matter when we're talking about Z mod 2 coefficients. Okay, right. So the idea is that, you know, until, I mean, so these invariants for a quadratic form, these Stiefel-Whitney classes had been defined long before. Maybe I should give the definition just something explicit. So here, if you take your quadratic form, you can always write any quadratic form over a field of characteristic not 2 as a diagonal form. So it's given by, in general, given by a symmetric matrix, but in this case, a diagonal matrix associated to kind of just n elements of your field. Then you could just write down what these Stiefel-Whitney classes are, and this is probably worth doing. So we have that the jth Stiefel-Whitney class of Q is the sum over all j tuples of numbers from 1 up to n of these products ai1, ai2 up to aij. Sort of hj of the field with Z mod 2 coefficients. Okay, and what does this notation mean? This is the notation for like a symbol in Milner K theory, if you like. So what I'm using is the fact that here h1 of the field with Z mod 2 coefficients is just in this situation f star mod f star squared, because we're in characteristic not 2, so this can be viewed as mu2 here. Yeah, and so basically a non-zero element of your field, like these numbers here, that gives you an element of H1, and then when you multiply j of them together, you get an element of Hj of the field. And sort of, you know, the theorem from the 1960s, I guess, is that this is a well-defined invariant of the quadratic form. So you could write your quadratic form in different ways in diagonal form, but these classes don't depend on how you write it. Okay, and then sort of the point is that Serre, you know, around 2003, by defining cohomological invariants, was able to finally make the precise statement that actually these are, in a sense, the only invariants that are defined for all quadratic forms of a given dimension. I should say there are more subtle invariants that are defined for some special class of quadratic forms, but it's still nice to have this statement. Okay, right. So, let's see. So maybe I should get on to the characteristic P aspects that I'll be talking about. Okay, so the question is sort of where should, let's say, cohomological invariants in characteristic P, I mean, so what I mean is what should be the analog of Serre's definition and everything when the base field of your group has characteristic P, so you like have, and the coefficients also have characteristic P. So the point is just, that's a situation that you sort of can't ignore. If you want to understand like quadratic forms over any field, you know, then you kind of have to take that case into account, where the coefficients of your invariants and the base field of the group are have the same characteristic. Okay, so the difficulty with this previous definition is that it's not clear what should étale cohomology mean. It's sort of, étale cohomology is sort of usually useful only when this number m is invertible in the field K. Okay, but the answer for the right thing to consider has been understood at least since Garibaldi-Merkuriev Serre's book in 2003, because Merkuriev sort of used the right definition in this situation. And that is that you should use what I would call Kato's version of étale cohomology based on differential forms. I call it Kato's version, although this had been studied in some form in the 70s by Bloch, Illuzi, and Mill. And in modern terms, this is now, we could now recognize this as motivic étale cohomology. So Vygotsky's, in some sense, it's just a different name, but I mean, puts it into a broader framework. So yeah, so one way to look at this is that, so in Vygotsky's theory, you can talk about étale cohomology of, say, any scheme with coefficients in sort of any abelian group with sort of any twist. And this is defined just for any abelian group A and any numbers I and J. So the point is, you know, whether, you know, A is finite or Z or even if it's Z mod P and X is over a field of characteristic P, Vygotsky's definition makes sense. And so you know, an incredible thing that Vygotsky proved is that if A is like Z mod L and L is invertible in the field, in the base field of X, then these just are the usual étale cohomology groups. But in other situations, like with Z coefficients, this is something different. And okay, so I want to focus on the case where we're in characteristic P. Okay, so how should I say this? So let's say a theorem about this, maybe in this form due to Geisser-Levine, but it's related to earlier work by Kato, I guess, is that, so for, let's say for a field K of characteristic P, if I look at étale motivic cohomology with mod P coefficients, then most of it is 0. So let's see, I'll just for shorthand write Hij of the field to mean étale motivic cohomology of the field with coefficients in FP twisted by J. Okay, then the point is that these groups are 0, except in a few cases. So let's see, Hii of K and Hi plus 1. Maybe I should call this like Hjj and Hj plus 1 comma J of K. So that's sort of quite different from what happens in if you're not in the characteristic P setting. And what's more, these groups have an explicit description in terms of differential forms. Let me just write this out. So moreover, there's an exact sequence, but relating. So this group you could view as Milnor K-theory of the field mod P, if you know what that is. But anyway, there's sort of, that may be one way to describe this group, but it has a more elementary description just in terms of differential forms, which is that you, it's maps into the group of differential forms over K. And here what I mean is this could be viewed as differential forms on K as an extension field of Z mod P, if you like. Right, okay, so just in commutative algebra, you can define the differentials on any commutative ring over, say, a field, and that's what I mean here. So the base field is like FP here. Okay, from that, there's a natural map to differential forms of degree J mod exact forms. And this map is called P. I'll describe it in a second. And then the co-kernel is this HJ plus 1J. Okay. Okay. And here, P is defined by, if you take one of the generators of this abelian group, by definition, well, I can write any element of this group as a finite sum of expressions of the following form: some element of the field times D of another element of the field over the same element, so on. I just define P of this expression to be A to the P minus A times the same product of sort of logarithmic forms. Okay. So, of course, it's not obvious that this map is well defined because there are various relations in this group, but in fact, if you map into there, it is well defined. Okay. Okay, so this is kind of an amazing thing because, yeah, as I say, I mean, basically differential forms are quite computable in a way that motivic cohomology or étale cohomology in other situations is not really as computable in a purely algebraic way. So in some ways, this characteristic P setting is actually nicer than the sort of mod L setting. Okay. Okay, so let me give a few examples. So like, say, H10 of a field of characteristic P is the same thing as just H1 of K with étale cohomology, K with Z mod P coefficients, because, well, I sort of did this calculation already. According to this formula, this just gives me another, I mean, this map P generalizes the map A goes to A to the P minus A. So this gives K mod instead of A to the P minus A. So I sort of showed this before. Another sort of meaningful case is H21 of a field of characteristic P. This is precisely the P torsion in the Brouwer group. Maybe I'll, yeah, actually there's some notation that goes with this, which is useful to introduce. So like, where does this isomorphism come from? Well, by definition, let's say the group HJ plus 1J of a field, in general, this is in some sense the more interesting of the two groups, I would say. This group is generated by a certain kind of symbols. So I write bracket, how do I write this? A comma B1 up to BJ. So it's sort of a weird kind of mixed additive and multiplicative kind of symbol. So A is an element of K. These other things are elements of K star. And the point is this symbol represents this differential form. Yeah, I think I'm correct in saying that. Okay, right. So this differential form lives there, and so this symbol represents an element there, and hence in this cohomology group. And so in that form, I can describe the isomorphism from this group to the Brouwer group. So I have to say that to describe this isomorphism, so this kind of symbol where A is in K and B is in K star represents a certain central simple algebra, so an element of the Brouwer group of degree P, central simple algebra, K with generators X and Y, modulo the relations that X to the P minus X is the sort of additive constant, P is B, the sort of modal constant, and Y X Y inverse equals X plus 1. Oops, excuse me. Right, so algebras like this give you elements of this Brouwer group. Okay. Right. Okay. So that's supposed to get you familiar enough with the kind of. So this is the sort of cohomology group where we're going to consider cohomological invariants. And I mean, I guess maybe these examples suggest that there's a reasonable place. These cohomology groups have some reasonable meaning. Okay, let's see. Maybe sort of one last thing is I should say like how the essential dimension is related to this. So maybe just for time, I will not try to describe the notion of essential dimension, but let's say it's a sort of a lemma here that if an affine group scheme G over a field of characteristic P has essential dimension. So if in some sense you can describe all G-torsors over any field whatsoever in any extension field of K in terms of at most n parameters, and even essential dimension at the prime P, which is in some sense the only relevant one for us. And let's see, and I guess if K is algebraically closed, then these I should say I haven't really defined what cohomological invariants are, but I mean you can talk about cohomological invariants with coefficients and with values in the sort of cohomology that I was just talking about, and you have exactly the relation that you would expect, that if you know the essential dimension of your group, then the cohomological invariants of your group are 0 in high degrees. I just have to get the numbering right. I believe it's like this. Yeah. Okay. Okay. No, sorry, I think, yeah. Sorry, maybe off by one. Excuse me. Okay, so let's see, H10. I think this should even be J greater than N, excuse me. I see, right, so yeah. Okay. Sorry, I think, yeah, okay, why don't I just sort of stop worrying about that? Okay, so this is sort of exactly parallel to what happens, in other situations. And so basically it says that the essential dimension of a group kind of measured its complexity. And so another way to look at that is that if you find that a group has some like high degree cohomological invariance, then you know that it's complicated. You know that its essential dimension has to be big. Okay, so an example where that comes in is this result by Reichstein and Vistoli, who showed that for any finite étale group scheme, G over a field of characteristic P, the essential dimension of G at the prime P is at most 1. Okay, this is a little bit disturbing. So in some sense, all finite groups, or slightly more generally finite étale group schemes, look kind of trivial if you look at them over a base field of characteristic P, and this means you're sort of willing to ignore field extensions of degree prime to P. They look sort of quite simple, and so that means that for this kind of group scheme, you're not going to have many interesting cohomological, invariants. Yeah. So let's see if I can figure out. Yeah. Somehow I think there should even be J at least n-1. That's what's confusing. So in this case, all these groups are going to have. Oh no, sorry. So for example, yeah. So the example, if I take G to be Z mod P, then we sort of have the invariance. There is an interesting invariant for this group in degree 1, 0. Yeah, so this should be, because this is just sort of H10 of your base field plus Ham from your group into Z mod P. This is sort of a general fact. And so, yeah, so for example, there's a non-trivial cohomological invariant in degree 1 for Z mod P. Right. Okay. So that sort of tells me how my numbering should go there. So, but you won't have any interesting invariance in any sort of higher degree than 1 for this group, or in fact for sort of any other finite group. So basically, well, maybe I won't try to describe their argument. Basically, it's sort of based on the fact that you could reduce the case of P groups, and then you use the fact that any P group has an action on some smooth curve that fixes a point, sort of a faithful action that fixes one point. Then just kind of by moving 0 cycles around on that curve, you can prove this, that somehow any G-torsor up to extensions of prime to P is kind of pulled back from a G-torsor over that curve, basically. Okay. so this sort of suggests that for some finite group schemes, this notion of cohomological invariance in characteristic P is sort of unavoidably not going to give you very much. Okay. All right, but let's see. So a sort of strange situation is that apart from examples like this where all the invariants are trivial, there were sort of very few examples of groups where anyone could compute all the invariants in characteristic P. So I should say that several people sort of have made computations of these mod P invariants in low degrees. So there's some recent PhD theses by Lourdeau and Wertheim, and both 2020, and then Merkuriev and his collaborators computed invariance in degrees 2 and 3 for several types of groups, typically reductive groups. So even in the original book by Garibaldi, Merkuriev, Serre, basically Merkuriev showed that the Ross invariant sort of, which lives in degree 3, works essentially exactly the same way in this mod P setting as it does in other settings. Okay, but somehow it's a sort of strange thing that there aren't so many examples where people could compute the sort of all the invariants for a given group in a way sort of parallel to Serre's result about the orthogonal group at the beginning. So that's, at least I wanted to do some calculations of that sort. I should say, though, maybe there was a kind of hope in doing these calculations that you would get some more information about essential dimension, and that didn't happen in my calculations. But okay, I still argue that it's worth starting on these calculations. So let's see. Because I have this sort of a general slide about the value of or the interest of this problem. Sort of, so these distinctive features of invariance in characteristic P, are they pathologies? Well, no, I agree that they are distinctive features. Like, for example, the fact that you can compute these kind of mod P cohomology groups so neatly in terms of differential forms. Okay, so there's that, and okay. So let me okay, begin to discuss sort of the basic calculation. So I want to start computing these mod P cohomological invariants for all degrees, at least in some for some groups. And let's see, yeah, sort of the basic calculation in my paper is what are all the invariants over any field of characteristic P for the group scheme mu P, for any field K characteristic P greater than 0. Somehow, basically, once I did this one calculation, then you could sort of build up to more complicated groups like the orthogonal group fairly successfully. But sort of this basic calculation was kind of painful. So let me sort of give the answer. It's sort of quite a simple answer. So let's see. There's one sort of basic invariant for mu P, which lives in H11, say alpha in invariant in degree 1 of mu P, just because, and this is sort of the obvious thing, that mu P torsors over field are just the same thing as elements of the multiplicative group mod P powers, and that is the same thing as this group H11 of the field, which as I mentioned, can be written as the first Milnor K group mod P. So that is exactly the same formula as this. Okay, so in other words, sort of this is, let's say this, if we think of it that way, that's the sort of obvious invariant for mu P torsors. They have an obvious invariant in there. And as you might expect, the conclusion of this calculation is that sort of basically that's the only invariant, or all the other invariants are sort of built out of that. So the kind of basic theorem is that yeah, every cohomological invariance for mu P and characteristic P has the form it's like some constant plus I should call it like C plus E times alpha for some sort of just constant C and alpha, meaning C lives in the cohomology of the base field, and E also lives in the cohomology of the base field, and they're going to live in different degrees because alpha here lives in degree 1, 1. Okay, so right. So in other words, it's just sort of all the invariants are built out of this sort of obvious invariant in the way you would expect. But unfortunately, this takes quite a bit of work to prove. So I sort of drew a kind of well, let me say a bit about this. So the idea was so how do you compute all the invariants for some group? So the sort of general idea, which works in characteristic P also, is to use the idea of versal torsors. So just to sketch this, what you do is if you're given a group, and if so, let's say V is a representation of my affine algebraic group over a field, over the field K where it's defined, and let U and V be a Zariski open subset, so that G acts freely on that open subset. So then U mapping to U mod G, that is a G-torsor in the world of principal G-bundle, in other words, in the world of schemes rather than fields. But you could restrict to the generic point of this variety, and then you get a G-torsor over a field. So you get a G-torsor over the function field of this quotient variety. And the sort of basic argument, sort of rather easy, is that basically every G-torsor over any extension field of K is pulled back from this sort of universal G-torsor. It's called a versal G-torsor. So in other words, this kind of acts like U mod G kind of acts like a classifying space of G in topology, but somehow it's only classifying space if you're dealing with G-torsors over a field. I mean, classifying spaces in topology would usually have to be infinite dimensional, but when you're only working over a field, then this works as a kind of finite dimensional substitute for the classifying space. Yeah, because of that property, we find that that sort of all the invariants for a given group are just they map injectively into the cohomology of this one particular field. So just because, I mean, if you have a cohomological invariant for G, it gives you an invariant for this particular G-torsor, and therefore an element of this cohomology group. And right, so you can sort of reduce or get some information about this by just computing the cohomology of this particular field. Now, unfortunately, this group is rather big in general. It's sort of probably much bigger than this, but we can say a lot about sort of where these invariants have to map into there. So, one, we know various things such that any invariance gives a cohomology class on the function field of U mod G, but it really, which is unramified on this variety U mod G. So in other words, maybe I won't go into too much detail, but we have this sort of quotient variety. If you have any codimension 1 subvariety in that quotient variety, then this cohomology class is unramified on that divisor. So that's one thing we know, and also Blinstein and Merkuriev observed that we know something else. I should say that if you're in the sort of mod L situation, then this information is sort of almost all you need. In the mod P situation, you need another observation, which is by Blinstein and Merkuriev, which is that there's sort of two projection maps from U times U mod G to U mod G. And when you go from this, when you pull back this universal G bundle, these are just the two projections. When you pull back this G bundle by those two maps, then you get isomorphic G bundles over this thing. I mean, in both cases, the pullback is just U mod U mapping to there. And so that tells you that sort of any cohomology class here that comes from an actual invariant, it must have the property that when you pull it back by these two maps, you must get the same thing. So say an element in the cohomology of U mod G, or this function field, is called balanced if it's two pullbacks to the cohomology of this sort of double product are equal. And what I'm saying is that it's somehow by rather easy arguments, any invariant has to give you a balanced cohomology class here. And Lichtenstein and Merkuriev actually showed that the converse is also true, that the invariants are just equal to the group of balanced cohomology classes there.
Can I ask a question?
Yeah.
Is it supposed to be obvious that the invariants inject into the H star star of K, U, or G?
Yeah, right. I mean, it's not totally obvious, but I mean the sort of the basic reason why it's true is
I guess what's confusing me is that the K, well, maybe it's not. Right. What's not obvious to me is that the K, U, or G is you're just looking at the one, just at the function field.
Right.
And it's not clearly what's going on if you.
Right. So you might have a field that maps into some sort of lower dimensional subvariety.
Yeah, something like that. Yeah.
I mean, that's a kind of issue, but I mean, basically, that's an issue which sort of like Serre and the others took care of in their book. So somehow, basically, you can go from talking about fields to talking about like arbitrarily small open subsets of U mod G, and so you can make that work.
Okay.
But good point. Right. So, okay, then I sort of outline the way the rest of this proof goes here. Okay. So, right. So to make this calculation for the invariance for mu p, the kind of basic calculation, I needed this sort of general description, which this I should say works the same whether you're talking about mod p cohomology or mod L cohomology. Another thing is, so for mu p, these quotient varieties that I look at are just going to be like one dimensional. It's basically just the multiplicative group mod mu p. But that means that I sort of have to understand the mod p cohomology just of something like the function field of P1. You know, I have to understand the mod p cohomology of sort of fields like K of X in terms of the cohomology of K. And this is one of the ways in which this mod p situation is a bit messier. The mod p, the mod L étale cohomology of K of X is not that bad. It's easily describable in terms of the cohomology of K. And for the mod p cohomology, it's also describable, and that was done by Bolden. But it's sort of much kind of bigger. There are these sort of, because of the phenomenon of wild ramification, basically you can describe the cohomology of this, but it's much bigger. But nonetheless, you know, somehow with work, you can argue that because this description is explicit, even though it's huge, you can determine which cohomology classes are balanced, and therefore, you know, end up with a computation of what are the invariants for this group scheme mu p. And somehow, yeah, because the answer is sort of uniform, it sort of doesn't depend too much on the base field. You can also get from that a description of the invariance for like basically mu p times any other group scheme. If you know the invariance for some other group scheme, then you can just read off the invariance for mu p times that, and so as one of the basic calculations, you can compute the invariance for these sort of abelian group schemes like this. Okay, and I should say maybe now that I want to go from there to the orthogonal groups as one of the classic calculations. So the point is that, right, so let's see. So let's say Q0 is a quadratic form, non-singular over a field of characteristic 2. Then let's see, so what are the mod 2 cohomological invariants for the group scheme of Q0, or in other words, yeah, that's the same thing as asking what are the cohomological invariants for quadratic forms of dimension n. I should say that the orthogonal group, basically because any quadratic form becomes trivial after an extension of odd degree, the orthogonal group is only going to have sort of mod 2 cohomological invariants. It's you don't get anything interesting by looking at like mod 3 invariants. So basically, if the field did not have characteristic 2, then this is a calculation that Serre did. But now I understand what happens if the base field also has characteristic 2. Okay, and so let's see. So the basic point is that there's an interesting subgroup z mod 2 to the maybe let's say 2n is the dimension. Say this is an even dimensional quadratic form. Then you can do something similar for odd dimensions. But there's an interesting subgroup in O2n, which maybe actually let's just say that. So let's say that Q0 is the direct sum of n copies of the hyperbolic form, where H is the hyperbolic plane, the two-dimensional quadratic form. So that's a homogeneous polynomial in two variables, and I mean the polynomial q of xy equals x times. Right. So the point is that because it sort of doesn't matter what Q0 is, the torsors for this group just are the same thing as the isomorphism classes of quadratic forms of dimension 2n. So I could just replace Q0 by this fixed form, by kind of the nicest possible quadratic form, and the invariance will be the same. Okay, so the point is that in the isometries for this quadratic form, you could switch the two variables, so that gives you an embedding of z mod 2 into the orthogonal group for the hyperbolic form, and you could multiply x and y by the same square root of unity, if you will, and that would also preserve this. So you get an embedding of this group into this orthogonal group, and hence because obviously the product of n copies of this group maps into there, you get this interesting subgroup in this orthogonal group. This is sort of parallel to the fact that the orthogonal group O2n contains the subgroup z mod 2 to the 2n, corresponding to like plus or minus ones down the diagonal. But somehow in this characteristic 2 setting, sort of plus or minus 1 becomes these two different group schemes. Okay, and this is a good subgroup to consider because, let's see, because basically all the torsors for the orthogonal group come from torsors for this group. Let's say H1 of a field with coefficients in this subgroup. Then this maybe surprisingly maps onto torsors for the orthogonal group. This is a sort of, I mean, a standard fact. How should I put it? Like in the case of the orthogonal group, sorry, if we were in characteristic not to, this would sort of be saying that every quadratic form can be diagonalized, and here we're saying something sort of parallel to that. Let me sort of spell it out. So basically, if you're given sort of an element of my field, that maps to, I can view that as a z mod 2 torsor because this is f mod elements x squared minus x. And if I have a non-zero element of my field, then I can view that as an element of, as giving me a u2 torsor because this is f star mod f star squared. And sort of given these two numbers, you can just write down a two-dimensional form, sort of a and f together determines the two-dimensional quadratic form. Let's see if I get the numbering right, something like b times x squared plus xy plus ay squared, I believe. And it's just a fact that that every two-dimensional quadratic form can be written in this way for some values of a and b, and that's saying that this map is surjective in the case where n equals 1. And further, like any a sort of analog of diagonalizing a quadratic form is that any two-dimensional quadratic form can be written as an orthogonal direct sum of n two-dimensional forms. So you can't quite write it as a sum of one-dimensional forms like in the diagonal case, but almost as good as that. So I mean, I'm not proving this, but once you believe statements like that, then that's equivalent to saying that this map here is surjective, that you get every quadratic form by just writing down a list of n elements of the additive group and n elements of the multiplicative group. Okay. Right, so to finish this thought, okay. So basically, it follows then that if you want to analyze what are the invariants for the orthogonal group in characteristic 2, they're all sort of determined by invariants for this subgroup. Let's write it like this: the invariants over my field of the orthogonal group, say for this hyperbolic quadratic form, that just injects into the invariants for this rather simple group. I didn't really spell out, yeah, well, but but sort of these invariants we kind of know very well. They're just sort of like any invariant basically is a linear combination of the sort of obvious invariants. Z mod 2 has an obvious invariant in sort of, you know, there's sort of an interesting invariant in degree 1, 0 for Z mod 2, and there's an interesting invariant in degree 1, 1 for mu2, and sort of all the invariants for this product are just sort of, well, built up from these basic invariants in a kind of obvious way. So, right, so at this point, to figure out exactly what this subgroup is becomes a kind of elementary problem. Let me just write a little bit about how that goes. No, actually, maybe I should write the, so yeah, how should I put this? So like sort of any invariants for quadratic form in characteristic 2 for quadratic forms of dimension 2n can be written in some way as like, so my notation, my invariant of a sum of n these two-dimensional forms, bi times ai, so this is that constant times this two-dimensional quadratic form that I wrote down here. So sort of just by this embedding, in other words, you have to be, any invariant must be writable in the form sum of, like, this is a bit of a mouthful, some constant cohomology classes times some product of the b's in the sort of, this is in the sort of Milner K-theory part of motivic étale cohomology, or it could be some of the b's times one of the a. Am I drawing this right? Yeah. Yeah, some of the b's times one of the a's. Okay, because one of the features which I didn't really emphasize, because there are sort of somehow so few of these cohomology groups which are actually non-zero, you can multiply sort of any. The way it works is you can multiply any number of kind of elements of the multiplicative group, but you can only multiply one copy of the additive group. Somehow, when you multiply like H10 of a field times H10, you land in H20, which is just 0 in this situation. So any invariant has to be sort of writable in terms of these non-zero numbers and these, these elements of K star, these elements of K. But somehow there's this limitation, which you sort of wouldn't see in other situations, that you only have one copy of the additive group there. And then what you find is, so any invariant can be written this way, but on the other hand, in a lot of cases, you can argue that what I've written down there is sort of obviously not well defined. Like, for example, because it would change if I changed the order of these terms or something like that. So it's rather easy to go from that to actually finding which invariants are really, which expressions like this are really well-defined invariants of quadratic forms, and the answer is rather little. So basically, every cohomological invariant for an orthogonal group in characteristic 2 is a linear combination of just two very obvious invariants, sort of, I say, one, the discriminant, or what you might call ARF invariant in H10, and the Clifford invariant, which lives in the Brauer group, H21. So it's a sort of discouraging situation where somehow at the end of sort of this whole argument, you find that there are sort of many fewer cohomological invariants than you might have expected by, yeah, I should add that in terms of essential dimension, the orthogonal group looks kind of reasonably complicated. Like the orthogonal group of dimension 2n has essential dimension n+1. So it looks like it could, from that, it looks like you could conceivably have cohomological invariance as high as this dimension. And that's kind of roughly what does happen in characteristic not 2, where the Stiefel-Whitney classes are enough to give you, to give you the optimal lower bound for this essential dimension. Okay, but it's sort of a strange feature that, okay, at the end of doing this calculation, there just aren't that many cohomological invariants. So, okay, so nonetheless, I guess, so I also did this calculation for SON, and I guess sort of similar results. There's sort of a few more invariants in a few cases, but let's see, it still doesn't seem sort of so impressive for giving you information about essential dimension anyway. For the spin group, for at least for n at least 10, things are a little bit better in that we have cohomological invariants in degrees 4 or 5, which in each case give the optimal bound for the essential dimension. So, you know, maybe this is just a fluke that sort of these particular groups, the spin groups, work well for this purpose, but in characteristic 2, I mean, you know, but I guess one just has to sort of compute further. I mean, another question one might ask is, which I think Zenobia has asked me before, is does this mean that you should consider some other invariants in some other kind of like mod 2 cohomology theory in this case, or mod P cohomology theory in general? And I don't know. I mean, it's sort of hard to think of any other theory that is sort of so natural as this. But of course, you know, if you think of the problem as how to justify this result and to prove other results, then maybe you have to look at other cohomology theories. Okay, I'll stop there.
Thank you very much. Let's thank speaker. So, is there any question? Any question? Any question?
What do you get for symmetric groups?
Well, I mean, in some sense, not much, just because of your theorem, you know, because let's see, you know, because the essential dimension, you know, is at most 1. You're sort of not going to get any invariance above degree 1 anywhere, at least over an algebraically closed field. So you will have this invariant in degree 1 just because as the symmetric group maps onto Z mod 2, that gives you an invariant in degree 1. But in a sense, that's it, you know. So it's sort of a sad story. But I mean, but in that case, clearly inevitable, right? Because, you know, the essential dimension at the prime 2, if you're in characteristic 2, the essential dimension is just 1. So yeah, you sort of can't have any interesting invariants.
So, more questions?
Yeah, I have a question. If you have something like a classical or sort of algebraic group over a field of characteristic P, is there any sort of relation between cohomological invariant of the group itself and the cohomological invariance of the Frobenius kernel?
Yeah, I don't know. I mean, I guess it's, we're going to say it seems like a reasonable question. Yeah, I mean, yeah, I haven't thought about it at all. I mean,
so so for example, if you take the Frobenius kernel of the orthogonal group, you don't know whether in characteristic 2, whether that's what the cohomological invariants of that are.
That's right, or the essential dimension. It could also be interesting, but yeah.
Okay, sure. Thanks.
I guess, right, there is this, in some sense we know that actually the essential dimension is pretty big, because there's, I mean, maybe you know this, that sort of if you have like a finite group scheme where the tangent space has dimension n, then isn't there this result that the essential dimension has to be at least n in that case? So the essential dimension has to be pretty big.
More questions?
Well, maybe I'll ask. So for spin, you said, so what do you know for spin about cohomological invariance just in general?
Oh, I see. I know. I don't know anything in general. It's just that sort of, you know, I kind of was able to write down like one cohomological invariant that, you know, had pretty high degree and turned out to be optimal. But yeah, I didn't try to do the whole calculations. You know, who knows? It's anyway. I didn't try.
Does this cohomological invariant exist for bigger n, or is it just up to 10?
Oh, I see. No, in these arguments, yeah, it's all kind of like ad hoc. I mean, sort of like low-dimensional quadratic forms. Obviously, there are all kinds of, you know, tricks you can play, and right. So it's totally unclear, yeah, what exists in the spin group for higher n. It's sort of actually in that case, it's the same situation in characteristic not 2, right? Like nobody has any idea, I think, what are sort of all the cohomological invariants of the spin groups, except in pretty low dimensions.
Okay, so More questions? If not, then let's thank the speaker for a wonderful talk. Thank you very much. So we will resume in a week at the same time. Thank you, everyone. Have a nice weekend.
Okay, thank you.
Bye all.